they said they cannot see the blackboard, but I really don't know why.
The cameras are focused. This happens sometimes.
I don't know how to refocus the camera. Do you?
Sometimes if you just turn it off and turn it on, sometimes it just comes back. You just like in the meet, if you just turn it off.
I'm not going to write on the blackboard anymore, I hope. So I think you can just deal with the presentation. Can you see the presentation now? I hope you can. So let's just stick with this online version. I'm really sorry about this. I know Maria does her classes from home, from the not from home, but from upstairs, and I do my classes completely on the blackboard in my other courses. So I have never done this mixed thing. Doesn't seem to work very well. In any event, what I'm going to talk about is just this integral, this equation 2 of 1. So he does this symmetrically from one end of the segment to the other end of the segment, and then he simply got rid of the vector nature, this alpha angle, and then what he does is he replaces this alpha angle, which would be here in this corner, with this other angle, which is up there near the observation point. So he goes from the alpha angle, which is at the current, to the theta angle, which is at the observation point. And the relation is simply the sine of alpha is the cosine of theta due to geometry. And also, the cosine of theta we can express as r over the square root of the Pythagoras law. And he also changes over the integration variable, which is very useful for these long wires. Whenever you have long wires, this is what you should do. Instead of a lengthwise integral, do an integral in angle. It usually works better. And he does that. And what he does is he uses this relation that the tangent of the angle is L over R. So he gets the relation between the infinitesimals, the dl becomes d theta multiplied by r over cosine squared. That cosine squared here's the other cosine squared that we get from over there. And so we retain the cosine of theta, which equals x here to integrate, which was the sine of alpha. Okay? And then the integral is fairly trivial, and here is the result. And then he has to introduce the geometry that he actually went from r to minus r, and so this numerical factor that we were looking for is just square root 2 over pi. But we have the mu0 current over r in the z direction. So most of the exercise was trying to get this numerical factor. The second problem is about this loop. When we look at this loop, which consists of two quarter circles and two line segments, is to realize that the two straight line segments will not contribute because the vector product will vanish since the current is parallel to the observation direction. So all we have to deal with are the circular segments. For the circular segments, we don't need to integrate, right? Because the dl and the observation vector are perpendicular, so there is no angle problem between them. And the length, the r minus r prime squared, is also constant. So we will have to multiply simply by the length of the segment. The two segments will have opposite signs because the current runs opposite. Taking all this together, here is the result. Again, we get the mu0, the current, the z direction, and then instead of just 1 over r, we get 1 over 8 minus 1 over b, and the numerical factor is an 8, because the 4 pi is killed by the 2 pi over 4. Over 4 because it's just a quarter circle. That's how we end up with an additional factor of 2. In the last example, which is a semicircle and two long lines, all the contributions point to the same direction, right? Because it's still a sort of a closed loop, even though it's closed somewhere far away. So all the contributions are in the same direction, quite opposite to the fact that happened in the second example. And it's just a superposition of a semicircle, which we get the same way as we got the quarter circle, factor of 2 larger, and the sum of the two infinite half lines, which again are easy to get if we use the sort of angular integral that we employed for the line segment. Except now one of the limits has to go up to 90 degrees. So we integrated the theta angle from 90 to 0. And then when we get that, which is done here very nicely, again we get V0 current in the z direction over r, the only distance in the problem, and then the numerical factor, which is pi plus 2 over 4 pi, right? The pi comes from the half circle, and the factor of 2 comes from the two line segments. So that was the homework assignment. I'm sure all of you did it perfectly well. And now let's turn to the new section, which is about magnetostatics. It's about magnetism. You can see this presentation, right? Let me ask. Anyone? Did you see the PowerPoint? Okay. I'm not going to go into presentation mode because it's easier for me. I hope it's not too small. You can see. So the plan for today is to cover the first few points, first 2 or 3 points. We are talking about magnetostatics. So we are talking about magnetism. That is something we are all familiar with. Ever since we were teeny tiny toddlers, we played with magnets, right? Most of the toys, maybe not for babies, but for small children, come with small magnets. So we are all familiar with magnets. Magnets also play a crucial role in our modern civilization. Most of the electrical energy is produced using magnets, right? Because all the turbines, all the dynamos, they have a rotating part which uses induction from the next topic in this course, Faraday's law, to generate electric voltages from some movement. So we do need magnets all the time. Most of our technology is based on magnets. It's based on magnetic recording. Nowadays, you can get a nice computer or a nice cell phone without a magnetic recording in it because you use solid-state drives, right, which uses capacitors. But throughout the 90s, in the 2000s, it was all magnetic recording, and that's what gave us this huge boost in information technology that we suffer today. I will try to talk a bit more about magnetic recording. But also, as any good talk, versus solve starts in ancient Greece, right? So some 3,000 years ago, some pastor out in the fields in the province of Magneto, as you have all heard the stories, were playing with some rocks, and they behaved funny. They got attracted to each other, and they repelled each other. So that was a material today called magnetite, iron oxide, and it's magnetic. All this magnet comes from the name of a province in Greece. And also, when we were small children in primary schools, the idea of forces, attractive forces and repulsive forces, this was explained to us in terms of magnets, right? The North Pole and the South Pole of two magnets attract each other, two North Poles repel each other. So we are all very familiar with the idea of magnetism. Now, we are in physics, second year, hopefully, and you can ask yourself, they told us about electrostatics, about electrical interactions, also repulsive or attractive. They told us about gravity. about other forces like surface tension, van der Waals forces, all sorts of forces, which they taught us fairly well how they work. So maybe we don't understand all the details now in second year of physics, but we have a reasonably good idea of what's happening. Did they ever tell you how a magnet works? Why a piece of material is magnetic? They did not. And why is that? That's because magnetism is really difficult. It's one of the most difficult subjects in physics. Do you think that I will explain to you how magnetism works in this course, maybe today? Probably not. This course is about electromagnetism, so we deal with the effects of magnetism. So we will deal with Faraday's law, that's nice. We will describe how a magnetic field is created by a piece of magnetized material. So we will learn more, we will get a better handle on magnetism, or the effects of magnetism, but we will still not learn what is magnetism, why is a piece of material magnetic, how can I change its sort of magnetism, because that is really hard. You will probably not learn much about it throughout your core physics career, a little bit in solid-state physics and some specialized courses, but it doesn't subtract from the importance of magnetism. We are surrounded by magnetic phenomena all the time. So let's just start to look at magnetism. To be able to deal with all these magnetic phenomena in electromagnetism, we need a sort of macroscopic description of the effect. So we will hide all this important stuff, all this microscopic physics that we don't know about yet, and I will not explain to you either. We will hide all that in this M vector, the magnetization. The same way we hid the important microscopic physics of a dielectric in the electrical polarization. So remember, for electrostatics, what we did was assume that we can describe the electrical response of the material by looking at what the tiny electrical dipoles do inside it. And apply the electrical field, we polarize somewhat the molecules in a material. These will orient, they might interact a little bit. And all of this we can encompass in a polarization. And that polarization vector then gave rise to the D electric field. And that's where we start, because this is electromagnetism. The same philosophy applies for magnetism. We will assume that we can describe the magnetic response of a material in terms of the magnetic dipoles that it possesses that might get induced. These dipoles may interact with each other. They will respond to an external electric field. All of this we will hide under the carpet inside this magnetization vector M. Now what we want to look at is not how the magnetization M is born based on microscopic principles, but what sort of fields, D fields, it creates. Later we will introduce the H field, which really has the name magnetic field instead of the B, which is magnetic induction. And that is the same philosophy as between the E electric field and the D electric field. So physically, as far as forces are concerned, if I have a magnetic dipole and I place it in a magnetic field, a B field, that will create a torque. Instead of just a force, it will create a torque. It will try to rotate the magnetic field. This is why magnetism is so hard, because it doesn't deal with forces, which are sort of easier to sum up. It deals with torques all the time. So it's a second order effect. The first order effect is always electric, and magnetism is a second order effect. So it's harder to characterize. Nevertheless, it's very important. If you really want to understand if you really want to try to begin to understand how magnetism works on a microscopic scale, you need to use quantum physics, quantum mechanics. That is certainly not something that we can do in this course, but we can get a sort of phenomenological understanding of what's happening if we imagine every tiny magnetic dipole inside our material as a small circular current. So if we have a current loop, as you know, that creates a magnetic field, and that magnetic field can be described in the dipole limit, something you learned about. And this is the sort of dipole that we think about. So if you have an atom that has its electrons running around, they are sort of like a current. So we can think of them as generating what's called an orbital magnetic moment. And then, so that is still not too much of a stretch. That's quantum because it's an atom, they are electrons, so they are not truly like a classical current, but it's a fairly close description of a current loop. The more important part of magnetism, nevertheless, is created by the spins of the electrons. So electrons don't just have charge and they run around, they also have a spin, and that spin is what gives rise to most of the magnetic phenomena, and that is a purely quantum mechanical effect, so relativistic effect. So obviously we cannot have a handle on it, but we can hide all of that in the magnetization. We can group together the materials in terms of what sort of tiny magnetic dipoles they have inside. If you have a piece of material with no external field applied, and there are no dipoles in it, which is the case of most decent materials, a piece of paper, for example, or a frog, that would be called a diamagnet. Diamagnets usually do the following. If you apply an external field, that external field will induce a magnetic moment. It will induce tiny currents, tiny orbital currents, that will try to oppose the applied field. So the internal field will be smaller than the external field. It's usually a small effect, but still it's strong enough to, for example, levitate diamagnets. So if you have a big magnetic field, you work in some decent national laboratory, like in Tallahassee, and you have 30, 40 Teslas available to you, much larger than what you can find in Spain, for example, anywhere. Then you can levitate a frog. You just take a poor frog that you catch outside the laboratory, and you put it in your 30 Teslas, and then it will be flying around. That's kind of fun. And the frog does survive, so it doesn't even have to be a harmful experiment. The prime example of diamagnets are superconductors. Superconductivity usually is associated with being a perfect conductor. But that's not the important property of superconductors. What defines a superconductor is that it is a perfect diamagnet. So it expels all the magnetic field inside. The internal field in a superconductor is zero. It just does not want to let external fields enter into it. And being a perfect conductor is a consequence of this. The other group of materials, we can say they do possess tiny magnetic dipoles all the time. So they are called paramagnets. I usually use the word paramagnet for something that has these dipoles not ordered. When they are ordered, they can order in different ways. What we are used to are ferromagnets. So the tiny magnets on our fridges at home, they are ferromagnets. The magnets inside the motors, they are ferromagnets. That's what people usually call a magnet. There are other sorts of magnetism. The tiny dipoles, they may order in different ways. If they like each other, if they like to point towards the same direction, that is what a ferromagnet is. if they hate each other, they are just antisocial, and they want to point in different directions, in opposite directions. That would be an antiferromagnet. And then there are small changes even to this description, because not all those dipoles have to be equal. And then you have ferrimagnets and antiferrimagnets. Magnetism is complicated. Although these sorts of things you have with ferroelectrics as well. Also, since the dipoles are vectors, they may not even want to be pointing along the same direction or opposite direction. They may want to be perpendicular, right? Because you can have an interaction that goes with the vector product of the two dipoles. And that gives rise to even more complicated phenomena. It actually has the nice name of Joloshinsky-Moria interaction, so it's kind of scary to physicists, the Russian and the Japanese. And also, this is the sort of phenomenon that's very heavily explored today for magnetic recording. Because these spins that interact through this sort of cross product, they may create tiny magnetic bubbles that may be pushed along with very small energy investment, so very low consumption to move them around, to ride bits, the magnetic bits. And that is something we are also looking at. Paramagnets have the magnetic moment, but they are not ordered, so they just point along all sorts of directions. So overall, the magnetization in a paramagnet would be zero, as long as no magnetic field is applied to it. When we apply a magnetic field, the magnetization is born because the tiny moments in a disordered paramagnet will tend to point towards the magnetic field to a certain extent. Higher the temperature, the more they want to move around perfectly, so the smaller the magnetization. That's also very characteristic of paramagnets. The more we cool them down, the larger the magnetic response will be. And then this might become so large that at a certain temperature they order. And then there is a very characteristic phase transition. You have learned about phase transition probably in thermodynamics somewhere, maybe in this building, maybe back in your high school. So that is a very nice phase transition. It's a second order phase transition as you go from a high temperature paramagnet to a lower temperature ferromagnet or antiferromagnet. When the interaction between the spins or moments is stronger than the thermal energy. So that is how we can very briefly categorize magnetic materials. But we will not use any of this. What we will do is we will define a magnetization. So we will take whatever the magnetic moments do. If they are disordered, then this delta M, which is still a sum of quite a lot of tiny magnetic dipoles, will be zero. If they are ordered, like in a ferromagnet, then they probably have the same value. So then it will just scale with a small volume. And that's the same way you define the electrical polarization vector P. So the magnetization vector M is just the limit of this delta M over delta V. That's how we can conceptually define it. In this course, we will not talk about the tiny m's, we will always talk about the large m. So the units of the magnetization are simply magnetic moment over volume. The magnetic moment has volumes of ampere meter squared, right? Because it's related to a loop of current. It's the current running around times the area of the loop, and that will be the magnetic moment. And when we divide it by a volume, then the units of the magnetization M will be ampere over meter. It does not, unfortunately, have the same units as the B field. The B field has units of Tesla, which are not ampere over meter. And that's another complication of magnetism, that the units are all kind of complicated. And that's where the mu zero comes in, right? To take care of the units. Okay, so the next topic that we will look at is to try to calculate the B field produced by a piece of magnetized metal. But before I do that, let me just briefly, and without using my hands to show you anything, let me see if somebody will ask me questions from home. No? You can use your microphone as well to start me for questions. So let me go back a bit to this magnetic recording. So how does a hard drive work? You probably still have computers at home, like my computer has a hard drive in it. Probably your computers also. Hard drives are just small sheets of some piece of plastic coated with a magnetic layer. Some sort of alloy of iron, cobalt, and nickel, and whatnot. These days, more likely some rare earths. So some magnetic materials. In this magnetic material, you create small areas with a well-defined magnetization, the same kind of magnetization that we are talking about here. So these are ferromagnetic layers. You can orient the spins, let's say up or down, or left and right, and that is how you code your zeros and the ones. That's what the computer is, right? The zero and the one. So one direction will be called the zero, and the other will be called the one. And that you can do, and that you could do from the very first day of information technology, from the 50s, from the 60s. So information was always recorded on tapes, magnetic tapes. Actually, your internet traffic is still recorded on magnetic tapes. Google has the largest set of magnetic tapes hidden somewhere in Switzerland where they record all of the internet, because magnetic tapes still provide the densest and cheapest way to record petabytes of information, and that's what Google does. In your computer, nevertheless, you have hard drives which are not tapes; they are rigid. That's the only difference. So you could create these areas of small magnetization, and you could have created them quite small back in the 70s already. Nevertheless, when I started touching computers in the late 80s, early 90s, the first IBM personal computers, which were very similar to the ones today, they had, the largest ones had a hard drive of some 20 megabytes. Now 20 megabytes, if you think of it, is not that much, right? But if I give you a personal computer with 20 megabytes of storage, you will not know what I'm talking about, because your computer has terabytes of storage, right? Or hundreds of gigabytes. So several orders of magnitude different. And it is the same technology. It's still magnetic films with bits on it. The only difference is that the bits are smaller, so you can store more of them on the same size of a hard drive. Because the actual hard disk didn't grow. They actually shrunk over time, but the density increased. And the reason was not because it was so hard to create tiny bits. It was because it was so hard to read them out. The way the bits were read out in the 60s, in the 70s, in the 80s, was using induction. So they moved the disk around, it was spinning, or if it was a tape, it was just sliding along. Underneath a piece of coil, so again they used Faraday's law, and as that piece of magnetic material moved, it had its B field, something that we will calculate today, but the B field is created by a small magnetization. And that B field induced a voltage, as you will learn in the next session, but you all know about Faraday's law. Changing magnetic flux creates a voltage. And that voltage could be positive or negative based on the direction of the magnetization rhythm, so the direction of the beat. And that's how information was read out. And that is what limited the density, because this coil in which you produce the induction couldn't be made too small. If you made it too small, the voltage was too big, you got lost in the noise. So a new technology was discovered in the late 80s, and it's probably one of the fastest technology transfer examples, because within less than 10 years, IBM was selling new types of hard drives, and this was the phenomenon called giant magnet resistance, discovered by Albert Fert and Peter Greenberg, and they quickly got a Nobel Prize for it, and it gave a huge boost to information technology. Giant magnet resistance is the idea of using two magnetic films separated by some metal, which in a complicated method is something that we also looked at quite a lot in our group as well. It has the following property. The resistance of this piece of material, which is not homogeneous, it has parts magnetic, parts non-magnetic films. It changes based on the mutual direction of the magnetizations in one field with respect to the other. If they point along the same direction, the resistance is smaller. If they point along the opposite direction, the resistance is larger. Now, if the magnetic bit can modify one of the films, the magnetization of one of the films, because of the B fields that it creates, again, something that we will calculate today, that will change the resistance. Changing the resistance is really easy to measure, right? But that's just Ohm's law. If the resistance is different, I run a current through the reed head, the voltage will be different. So I have my zeros and my ones converted into voltage. And that technology, that reed head, could be shrunk down quite a bit. And that's what gave rise to hard drives that were hundreds of megabytes, maybe a gigabyte or more. Like by the turn of the millennium, you didn't have 20 megabytes of storage, you had a few gigabytes. And then the technology changed again, going from giant magnetic resistance to tunnel magnetic resistance, which only replaced the metallic layer between the ferromagnets with an insulator, with a very thin insulator. The physics was different, the geometry was the same, and it was much more sensitive, so you could keep on shrinking down the reed head. As long as you can keep shrinking the reed head, you can shrink the bits. Today's bits are so small, actually, that we bought a microscope called the magnetic force microscope, a very nice piece of microscope, for 200,000 euros, because why not? And we can't see them. So we have the best microscope available in the market to look at magnetic stuff, and what you buy in your favorite store for 50 euros has bits so small that we cannot visualize them. That's kind of an impressive technology, right? For 50 euros you get something that you cannot see even with 200,000 euros. That's the nice thing about physics, right? We can get to play with expensive toys. Maria actually has an even nicer microscope, a transmission electron microscope that can visualize atoms. I'm sure she has talked to you about it. And because she is much smarter, she could spend much more money. So she spent 5 million euros on that microscope. It's right here on campus. And because she's really smart, she got 2 of them, right? If you can buy one, why not buy 2? So that was not thought to look at magnetic stuff, but Maria jigged it because it's her microscope, so she can modify it, right? And if it breaks, it breaks. And it did break, but she can look at the magnetization of individual atoms. And that's quite something. That is still well beyond what magnetic recording is capable of today. So there's room to shrink, there's room to keep growing the magnetic recording, but it's becoming harder and harder. So people play tricks. They combine the way they write, the way they read. For example, we looked at the phenomenon where we can have the magnetic writing with light. The nice thing about magnetic recording is that it's stable. Your solid-state drive seems to be stable, right? You write that file onto your solid-state drive, and a year, 2 years later, it will still be there, hopefully. But it doesn't last forever, because it's based on tiny charges, tiny capacitors, and those charges leak out with time. Also, whenever you read a bit from your solid-state drive, you have to remove all that charge, so you destroy your information, you have to write it back. It's also kind of wasteful. Magnetization is there forever. The magnetic beads don't tend to move around, they don't tend to jump, as long as you have prepared them properly. It's also very cheap to read them. And the question is whether you can write them cheaply. And when they become small, it becomes harder to write, and this is why we try to invent this trick, easing the writing process with light. In any event, that's enough chit chat. So let's look at the fields, the B fields that produces a piece of magnet. So we can think of our material, which would be this egg-shaped thing, as broken up into tiny pieces. As usual, we will try to do an integral. So we break it up into tiny cubes. Each cube positioned at R prime, we have a volume dV prime, and the magnetization locally, M, at the position of R prime. All these the magnetization doesn't have to be homogeneous. It can vary throughout the volume, in direction and in value. What we ask for is the value of the B magnetic field that corresponds to just this piece of egg, this piece of magnetized egg, somewhere inside or outside the egg, usually outside. So we have to do a sort of integral. We have to find out what the B field is due to one of these little cubes, write it down, and then sum up for the volume of the egg. Instead of the B, what we will do is we will calculate the A, the vector potential. So again, this is the same sort of approach that we did in electrostatics, but now instead of calculating the potential phi, we calculate the vector potential A. Again, this shows that magnetism is more complicated because we deal with the vector potential. For an isolated dipole, for just one of these cubes, we have seen what the vector potential is. So any dipole, a piece of current loop, would create this dm prime. It creates a vector potential that has to do with the magnetic dipole moment, m, or dm, when we talk about the small one, the direction vector, and the square distance. Again, the distance is cubed because instead of the unit vector of direction, we use the full vector of direction. But it's a square node, just like Coulomb's law. So that's what creates the dA here. The vector potential due to one of these small cubes is dA, created by the magnetic material at R prime, which is dm prime, and then we have the integral. And the relationship between dm prime and the magnetization m, which again may be inhomogeneous, is simply dm prime equals m times b prime. So instead of summing up A, or instead of summing up the m prime, the small m prime, we can turn that into a volume integral. Eventually, we always need some sort of a line integral, surface integral, or volume integral. That's the only integral that we can actually carry out. But it's often easier conceptually to just write down that the vector potential A at the position R will be the sum of all the contributions dA, where we run around the whole volume. Each one of the cubes creates a dA at the position of R, but the cube is at R prime. So then we substitute this formula using this other relationship here as well, and then we get our usable formula. So we have the P factor, mu0 4 prime, as always, and then importantly, we have the cross product of M taken at the position R prime. R prime is somewhere inside the material. The direction vector R minus R prime, the square distance R minus R prime cube, and all of this is integrated over dV prime. So we have to go through the whole volume of our material. Now, that's it. We have the vector potential. We can calculate the B field by taking the rotation of this. We want to chew on this a little bit. So what we do is we employ some of our favorite relations. First of all, the R over R cube, this one, can be turned into a gradient of just 1 over R, as we know from electrostatics. We can decide whether we use the gradient deriving the R prime variables or the gradient deriving the R variables. Since the position of observation is fixed, it doesn't seem to make much sense to take the gradient with respect to R. We will take it with respect to R prime. Another relation, if we have the divergence of a vector multiplied by a scalar function, this is capital A times the lowercase a vector, that we can write as the potential times the divergence minus the cross product of the vector times the gradient of the potential. Again, the vector will be m and the potential will be this 1 over r. Also, we have a relationship similar to Gauss's law. If we deal with the rotation of a vector, the volume integral of the rotation of a vector, if this was the volume integral of the divergence of a potential, then we would turn it into the divergence of a vector, we would turn it into a surface integral of the vector simply, right? So something similar happens here, but again, because of the vector nature, it's not as simple. If we have a complete volume integral of a full rotation, that is equivalent to the surface integral integrating over the surface of the material of just the vector, but not with ds, but with the vector product with ds. So it's a bit more complicated, but it's the same idea. It's still sort of Gauss's law. So this relation we will use for the surface of our material. So let's try to apply this. So our vector potential A, we take the prefactor, and then we replace the R over R cube with the gradient of 1 over R, right? That's the first step. And then what we do is we use you can call it an integration by parts, or you can simply call it the derivative of a product. Let's say you have two functions, f and g. The derivative of the product, where g is the sum of the products of g times f derivative plus f times g derivative. The same thing happens here, but the other way around. We have the derivative, the gradient of 1 over r. Instead of using that, we pass the derivative over to the product, which is the second part here, so that will be m over r, and we also have the 1 over r times the rotation of m. Again, the derivative is not so simple because it's a rotation, but the idea is similar. And with that, we end up with two contributions. The first one we leave untouched, so it's just the volume integral of the rotation of m over r, and the second one turns into a surface integral. As we have seen, here we have the volume integral of a full rotation. We turn it into a surface integral, so there is no more derivative here. Now, the first term looks very similar to Ampere's law, right? So the vector potential is just J over R. It's quite habitual to call this rotation of M as a magnetization current. It's a volume term. A current, we think of a current as electrons or some sort of charges moving around. There's nothing moving around here. It's magnetostatics, but still you can pretend as if there was current throughout the volume, and then we can forget about the magnetic moment. Of course, at the surface, we have to be more careful. There is also a surface contribution. The second part is equivalent to having a surface current. So the idea is that if I have a piece of magnetic material, I can just, and I know the magnetization. Okay, so that's where we start from. I know what the magnetization is. All I want to do is find out the magnetic field B through the potential vector A. I can forget about the magnetization. I can replace it with these fictitious currents, the magnetization current, the volume current Jm, and the surface current Km. And this is the recipe how to do that. And then, once I have these currents, these fictitious currents, then I can just use my ordinary formulas. I'm good to go. So these are bound currents. It's the same idea that we introduced bound charges from the polarization. Remember that the divergence of the electric polarization P turned into bound charges and bound surface charges. Right? So, if you imagine your tiny magnetic dipoles M as tiny current loops, one next to the other, I have two equal tiny M's separated by a little distance. The current running around on one side will be exactly cancelled by the current running around on the other side where they touch, as long as the two tiny vectors are equal. So, if I have a homogeneous magnetization, I don't expect a volume current contribution because it will be all cancelled out. And this is what's reflected by the fact that this volume current Jm turns out to be the rotation. Only the derivative counts. If the M changes in the volume, and doesn't just change, but it has a rotation, then I will have this sort of current contribution. However, if the dipoles are the same or they don't change much, then I don't have this volume contribution. The same thing happened with the electrostatic dipoles, right? So if I have a molecule which separates into a positive and a negative charge, and next to it there's another one, and they are head to tail, the positive charge separated from one and the negative charge separated from the other will cancel out, and I have nothing there. So there is no volume polarization in a homogeneously polarized piece of dielectric. Nevertheless, at the surface, this cancellation doesn't happen, right? So that's why I got the surface bound charges, because the last molecule that will have its positively separated charge on the surface on one side, and the other last molecule with its negative charge sticking out to the surface, and that turned out to be the surface bound charges. The same thing happens here with the bound currents. Even if I have the same tiny dipoles, small m, and they cancel out everywhere their volume current J, at the surface this cancellation doesn't happen. So I will have currents, and these currents are perpendicular to the magnetization. And of course, they must be perpendicular to the surface normal, which here is called U of n. So U of n is a unit vector sticking out of the material, and that's how I get my surface current to be inside the tangential in the surface of my material, and still perpendicular to the local value of the magnetization, to the local tiny dipoles. That's basically the physics that you can see here. So this is the idea of the bound currents, and formulaically, again, what we get is the vector potential. It's just the integral of J over M in the volume, and K over J over R, and K over R over the surface. I think here, this K we must understand as being the no, this is fine. So that's where we end up with. Once we calculate this vector potential, then we can set about to get the magnetic induction P from the rotation of A. So again, we can forget about the magnetization, and we can just deal with these currents, the Jm and the Km, and we can get the vector potential. All of this is quite similar again to electrostatics. We do an analogy. It's similar, but it's not the same because of this complication of the vector nature of magnetism. So the sources of magnetism are vectors. The sources of electricity are charges, which are pointy things. That's in my mind, that's the crucial difference. That's the reason magnetism is so complicated. So I'm not sure how much of the stuff Maria wanted me to talk about. Let's see if you have questions about this part, because I don't want to get too much ahead of myself. Questions, doubts? Not in the class. We have a huge crowd here in the class, freezing to death. How about home? I hope at home you don't have to have all the windows open. Any questions, doubts? No? Next week, there's no class on Tuesday, right? Because we can all go to the beach. Oh, no, we can't. Anyway, next Tuesday, we don't come to class. Next Wednesday, I think Maria will come and continue. And next Thursday, you will have your partial exam, right? So your midterm, let's say midterm exam. So you understand how the midterm works, right? It's about the topics covered before. You will get a few questions, and then short questions, and then a few problems. And you can do that from home, from the comfort of your home, and Maria will watch over you. Or you can come here, and if you bring something to keep your hand warm, then you might be able to write here. I will be here, so I will be in the classroom, and you can do the exam in the classroom. You will be able to use help during the exam, printed material, books, your notes, whatever you wish to. If you have your book in an electronic version, like I do most of my electromagnetic books, you can consult it on your computer. But you should not use the internet to make your searches, and you should certainly not talk to anyone during the exam. So during the exam, you should have your microphone and your camera available. If you use the same device for consulting your books as where your camera is, that's not a problem. So if your camera is turned on momentarily, you will not have to announce it each time. Oh, Maria, I'm going to turn off my camera for a moment because I need to look up an equation. So you don't have to do that. But it would be nicer if you could have, if for example, you could use your mobile to watch over you and look at your stuff on your computer or tablet or whatnot. That would make life easier. Also, you don't. So Maria will tell you whether she wants you to have your microphone turned on all the time or not. You probably should not use headphones, because then it's really hard to say whether you're listening to someone over your headphone or not. So try to get your information technology resolved in a reasonable manner. Okay, but the idea is that you should do the exam on your own. You should not have a big WhatsApp session about the solutions and whatnot. Any questions? Doubts? Suggestions? No? Then I think I will stop here, and we'll see each other, some of us, next week. Okay? Bye. Okay, here's a question. Someone has a question finally. I'm listening. Yes, yes, I will do that right now. I will take one Luis's solution and I will upload it to the composite file. Okay. Fine.